Hi everybody, this video is going to be about ordinary differential equations and how to solve some of them. Differential equation being an equation that involves the derivative of some unknown function, and the solution of the differential equation then is figuring out what that unknown function is. And by ordinary we just mean that that unknown function is a function of only one variable. So the first type of ordinary differential equation we're going to look at is the separable type. And so an ODE is separable if we can write it in this form. That is, that the derivative of our unknown function can be written as the product of two functions, one which is strictly a function of our independent variable and another function of y. If we can do that, then a little friendly abusive notation allows us to move all the y's to one side and all the x's to the other, and then this integral must hold. And then if we can evaluate these integrals and then solve for y and what comes out of them, then we'll have our solution to the ODE. So here's an example of a separable ODE, one that we can solve in that way. We can set up these two integrals to perform. Integrating gets us here, and then just a little bit of algebra allows me to get to this solution. Here's our general solution for the ordinary differential equation. Of course, it's still in terms of some arbitrary constant. We put in any constant for c there, and you'll have something that solves the differential equation. Now, if we had a little bit more information, an initial or boundary condition, then we can figure out the value of that constant c. In this case, we typically call that pair the differential equation together with the initial or boundary condition. We call those initial value problems or boundary value problems. So with this being our solution to that differential equation we just looked at, that's the general solution. And if we knew, for instance, that when x was 1, y was 2/7, we could find the value of c. Doing that, we find that c must be 2. And so for the differential equation with the condition that when x is 1, y is 2/7, then this is the particular solution for that. This is the one and only one solution that makes that differential equation true, as well as satisfies the initial condition. So that's separable ODEs. I'd also like to look then at something called linear ordinary differential equations. Linear meaning that while we might have multiple derivatives of y, so we could have the first derivative of y, the second derivative of y, that in our differential equation, none of those derivatives appear to any higher power, or we don't have the sign of one of the derivatives of y. Essentially, we can write it in this form. And there are some coefficient terms on each one of those different order derivatives of y, and those might end up being complicated functions of our independent variable, but just functions of the independent variable. So if we can write an ODE in this form, then it's linear. And we specifically want to talk about first order linear differential equations, and that just means that the highest power, the highest derivative we see is just the first. There are no second derivatives of y or anything higher than that. So if this is what we've got, it's linear first order ODE, and we can rearrange a little bit. We can divide everything in sight by a sub 0, which again could be some complicated function of x. But if we do that, and we're just going to rename some things, namely that a1 over a sub 0 is, we'll call that p, and f over a sub 1, we'll call that g. This thing at the bottom then is what's called standard form for a first order linear ODE. And now the question is, how can we solve this? How can we figure out a solution to this differential equation? Well, what we're going to do actually is multiply by some function. We'll call it mu of x, the integrating factor. And we'll see in just a moment what mu needs to be so that what we're going to try works out. But let's just say that there's some function that if we multiply everything both sides by, that it's going to make life better, and then figure out what it is in just a moment. So if we multiply that, multiply out the left-hand side, what we might notice is that the left-hand side looks like it could almost be the product rule applied to a derivative of two terms. Namely, that it would be the product rule looking at the derivative of y times that function mu. And the only thing that would have to be true for that to be the case is that this stuff in red, p times mu, would need to be the derivative of mu with respect to x. And if that's true, then that left-hand side is just the derivative of the product of y and mu, which is going to be really helpful for us in just a moment. So let's focus then on that differential equation that defines what mu is. So here it is again. What we need to be true is that d mu dx needs to be p times mu. If you think about it for a moment, that might sound like an exponential function of some kind, where the derivative of a function is some function of the independent variable times the function itself, and that's a good intuition if that's the one that you had. Turns out that this differential equation is separable, and so if we do a separation of variables, integrate both sides, what we find is that natural log of mu needs to be the integral of p, and so then that means that mu must be e to the integral of p. And so because we built it that way, if we define mu to be this, then here was our ODE before, our first order linear ODE that we have multiplied by mu, it multiplied everything in sight by mu. Because we built mu to be what it is, then that means that the left-hand side is just the derivative of y times mu. And so if I integrate both sides with respect to x, then on the left-hand side, we just get y times mu, lump the constant with what comes along on the right-hand side. And so we just have to be able to integrate mu times g. And if we can do that, then we can solve for y by just simply dividing both sides by mu. And so here we have a solution to our differential equation. All we have to be able to do is integrate mu times g and then divide by mu, and we've got an answer. So here's an example of a first order linear ODE. Take a few minutes and see if you can come up with a solution for this, and then we'll talk about it in class.